Very nice introduction and for the invitation to give the talk here. It's my second time in the Fields Institute, but that one was a long time ago. So I'm really happy to be back. So I'm going to talk about a work that is joint with Pigatti and Stern, and that builds up on some work that I've been doing for a couple of years. And I will discuss this Nonabelian Yang-Mills-Higgs and a Plateau problem in Codimension 3. So the talk is roughly divided in two parts. So I'll start with some background and motivation, and then I'll give you the statement of the main theorem. So two parts. Where is it? Oh, yeah. Thank you. Nice. Okay. So divided in two parts. So background and motivation, and then the main theorems. Okay. So without further ado, we can start. So in the late 19s, interactions between gauge theory and submanifold geometry really propelled gauge theory. And in particular, there's a notable mention goes to the work of Tian, in which, for instance, minimal submanifolds, so special objects in submanifold geometry, arise as possible degenerations at the boundary of some gauge theoretic moduli spaces. In particular, Tian was considering, the closure of the moduli space of smooth Yang-Mills connections, and some minimal submanifolds arise as possible degenerations of these sequences. There's also work of Taubes in the direction between this correspondence of gauge theory and submanifold geometry, in which he identified a certain dictionary between solutions of certain types of equations and certain submanifolds by passing to so-called adiabatic limits. So the notion of adiabatic limit is something that is very common in the jargon of gauge theory and physics in particular, and it just means that the system that we're considering depends on certain parameters, and then these parameters will go to zero or go to infinity. We'll move these parameters, and I'll make this picture very precise analytically in a couple of slides. And these distinguished manifolds in the case of Taubes were pseudo-holomorphic curves, and this correspondence will play a role in the main theorems that I'm going to explain later on. On the PDE side, a similar correspondence between certain solutions of partial differential equations and certain special submanifolds has been investigated since the 70s, in particular thanks to the school of De Giorgi. And the correspondence that I'm referring to is this correspondence between minima hypersurfaces and semilinear scalar equations, in particular this Allen-Kahn equation. These comes from the gradient theory of phase transitions. And in a nutshell, minima hypersurfaces arise as epsilon going to zero limits of certain solutions of scalar equations. And it means a correspondence, yes, that you can associate, you can find minima hypersurfaces using this method, and usually you can also do vice versa. Yeah, I will explain everything later on. Yeah. And so this correspondence between minima hypersurfaces and semilinear scalar equation in recent time has been at the center of a lot of progress, in particular, thanks to the work of Chodos and Mantoulidis and work of Gaspar and Guaraco on the behavior of solutions of the Allen-Kahn equation on closed manifold. In particular, Chodos and Mantoulidis were able to prove the so-called multiplicity one conjecture, so a relatively important conjecture in minimal surfaces. And Gaspar and Guaraco described very well the behavior of minimal surfaces in using this method. This Allen-Kahn side of the story is also part of a bigger picture, and another side of the story is this Almgren-Pitts min-max theory for the area function. So all of this to say that this correspondence between PDEs and submanifold geometry played a crucial role in recent times in our understanding of minimal surfaces, but also of semilinear scalar equations. Something similar happened in the 90s, especially thanks to the French school of Bétuel, Brézy, Hélin. And in particular, there's a similar correspondence between elliptic systems and minimal submanifolds of Codimension 2. And the main protagonist of the story would be, for instance, the already mentioned Ginzburg-Landau equation, but also these U1X equations. And again, this is a correspondence between certain PDEs, certain solutions of certain PDEs, and certain special submanifolds. And the question I would like to try and answer today is whether do we have similar phenomena in higher codimension, because this correspondence is for codimension 2. So the one that I've mentioned before was between minimal hypersurfaces, so codimension 1 object and certain solutions. This is in codimension 3, in codimension 2, sorry. And can we find similar phenomena in higher codimension? So in particular, let's start slowly, codimension 3. Of course, one would have like a very coherent theory in any codimension, but this seems to be out of reach for now.
The hypersurface, it's the correspondence with by level sets.
Yes.
And here is again level set.
Yes.
And you're
Exactly. You can have the correspondence is a very vague term because it means a lot of things, and I'll try to refine this question as we proceed in the talk. But it could be at the level of gamma convergence. It could be at the level of convergence of sequences of critical points, at the level of convergence of sequences of critical points that are stable. One could have a convergence of variables, convergence of the corresponding currents. So that this is up to interpretation at every stage of your problem.
Sure, but I mean,
this is also the level of the set.
On one side, you could mention two manifolds, on the other. At least the picture that I have is could mention two submanifolds of level sets.
Yeah, exactly.
In all of whatever.
Yeah, exactly. You should really have in mind these level sets, very similar to the codimension 1 picture. And so to answer this similar phenomena in codimension 3, I need to explain you what monopoles are. And I'll keep going back to this definition of monopoles later on. But
just make sure the meaning of the correspondence is you can find some like derivative equations such that it corresponds to the QSB one.
Yes, that would be one interpretation. But I'll ask a very specific questions, and then I'll try to answer that very specific questions. Exactly. In terms of like correspondence, for instance, Taubes actually identified a very precise correspondence. So it is really context dependent. I mean that you can think of correspondence meaning that there's a certain relation between these two objects. So consider the principal SU2 bundle over R3. Then a monopole is just a pair phi A, where phi is a certain section, of this bundle, so SU2 cross R3, and a connection is a Lie algebra valued one form, so an SU2 valued one form. And the specific requirement of being a monopole is that they satisfy this equation. So the dA of the star, the out star of the dA phi is equal to f of A, where these two elements are given by this term. So the dA phi is a twisted exterior derivative, and it is twisted precisely by this A term, while f of A is the curvature of the connection. And in the case, for instance, in which SU2 is simply replaced by actual differential forms, so real value differential forms, these A wedge A would not be there, so FA would just be the exterior derivative of A. So in particular, we'll call a monopole a pair phi A, so sections and connection, satisfying this equation. And I'll come back to these definitions again and again, so they will eventually stick. So these monopoles arise as particular dimensional reductions of instantons in R4. So one would like, what happened is that Donaldson and many others were interested in the Yang-Mills functional in R4. That was extremely difficult to understand. So one has to work under certain condition, and then monopoles arise precisely a certain dimensional reduction. So when considering instantons in R4 that have certain translation invariants. So they actually appear as a simpler version of Yang-Mills connections. But variationally, these objects are minimizers of the following functional that I will refer to as the SU2 Yang-Mills-Higgs energy, which is just the integral in R3 of the Dirichlet energy term plus the curvature of the connection. So how do we see that monopoles are minimizers of this? Well, we can actually see that there are solutions of the Euler-Lagrange equations, for instance. So if you were to compute the Euler-Lagrange equations of this functional, you would get these two, and you can actually quickly check that monopoles satisfy this equation. But you can also prove something more, that monopoles are the only stable finite energy solutions of this functional. Yes.
How much of this really depends on the SU2 bundle?
SU2 bundle.
How that really matters that top.
I don't know this statement if,
Or
if
maybe
it-
the last state.
yeah, that I don't know. That I don't know. But yeah, you can consider versions of the solution. Yeah, yeah. And the point is whether you can. Yeah. Okay. I mean, if you artificially define something like this for like any other type of bundle, then I mean, these would be the corresponding other Lagrange equations, so you would satisfy them.
Does this energy have any kind of convection properties?
Yes. Yes. Well, at least this term, but the curvature of the connection, I don't know. More questions? So monopoles are, so they satisfy this equation, okay? And variationally, they're minimizers of this energy. But they also have other interesting properties. So in particular, if you consider finite energy monopoles, their energy will be given by 4 pi times m times k. What are these values, m and k? M is the so-called mass, so it's the limit at infinity of this phi. Yeah, yeah, yeah.
They're minimizers, local minimizers, critical minimizers,
Oh, you can take minimizers over compact sets.
compact set.
Yeah, take local minimizers, for instance. Yeah.
So they can have different energy levels.
Yes, yes.
which
And
they
this-
do want.
Yeah, exactly. And this is precisely what they do. Exactly. So in particular, the energy is just 4 pi times m times k, where k and m are the so-called mass. So the mass is the limit at infinity of the monopoles. And k is the charge. So what is the charge? The charge is the degree at infinity of the monopole rescaled. So why is this interesting? Because this is telling you that the energy in a suitable regime, so if you normalize it by 4 pi m, this is quantized. So this can only take integer values, or at least natural values. And in particular, one thing that has been proven in recent time, so the School of Donaldson started investigating, is what happens in this large mass limit. So when m goes to infinity. Yes.
Is it clear mass? That it's right.
Sometimes it's a constraint. Sometimes no, and then for certain masses, you will not have monopoles, but it could be. So it's not clear.
You also have solutions that have different limits and directions.
No, I mean, I guess it should come with this definition that it is well defined at infinity. Yeah.
Restrict your attention to these kinds of
Yes,
solutions.
yes, exactly. And in particular, not only to this guy. So what you're asking is extremely important because as soon as you start moving the mass, something will happen. So in particular, this energy is quantized. So if you actually divide by 4 pi times m, so this energy is quantized, and the energy measure that you'll have, I mean, you can actually prove that in this case of R3, they're actually equal to this. And it was proven by Fadel and Oliveira that as you take this mass going to infinity, these measures concentrate at points. So Codimension 3 objects, because we're in R3, so they start accumulating at points. And I want to ask a more general version of this, essentially.
Nice.
Yes, yes. Like a zero current, if you want. This is a part of a more general phenomenon. But so this is the interest that I have for these objects coming from the minimal surface theory. So these objects accumulating over certain Codimension 3 submanifolds. But there's also more interest coming from the so-called program of Donaldson and Siegel, which says, and I'll define what these generalized monopoles are, that versions of these equations, so these generalized monopoles, arise in manifolds with special holonomy. So in particular, I want to consider two settings. So Calabi-Yau threefolds, these are 6-dimensional manifolds, and 7-dimensional G2 manifolds. So these are very specific settings, and the manifold here is special holonomy. And these analogs, so these generalized monopole equations also arise as critical points of the Yang-Mills-Higgs energies. And Donaldson and Siegel suggested that suitable counts of these generalized monopoles would provide enumerative invariance. So What do I mean by this? This means that as m goes to infinity, these objects, so these energy measures, will, and I'll come back to this again and again, will converge to, in the case of Calabi-Yau threefolds, they would converge to special Lagrangians, and in the case of G2 manifolds, they would concentrate at co-associative. The actual definition of special Lagrangians and co-associative is not really important at this stage. What you want to know is that these two objects will be calibrated by certain differential forms. So in particular, Donaldson and Siegel suggested that these generalized monopoles will allow you to essentially take an invariant in your 6-dimensional and 7-dimensional manifold and express it as a sum and product of invariants that are computed over the special Lagrangians or co-associative. And this is still very impressionistic, this program of Donaldson and Siegel, but this would be a sort of similar to what Taubes did with Seiber-Witten and Gromov-Witten invariants, but in higher dimensions and in the non-abelian case. And I'll give you the precise definition of what these generalized monopoles are. But this is all to say that part of the motivation comes from minimal surfaces, so trying to construct and understand minimal submanifold in higher codimension. But there's also this interest that comes from gauge theory and trying to generalize some of the works of Donaldson and Taubes and many others to manifolds of higher dimensions. So in particular, I can refine the question, and in particular, I can probably give an answer to what it means, a correspondence, hopefully. So is there a correspondence between minimal submanifolds of codimension 3 and solutions of these SU2 Yang-Mills-Higgs equations in this large mass limit? Or more precisely, can we have any type of correspondence at all between Yang-Mills-Higgs energies and the codimension 3 area functional? And the answer is yes, in the following framework. We can prove, and I'll show you the statement later on, that these SU2 Yang-Mills-Higgs energies, so this family of functionals indexed by the mass, converges in a natural sense to the area functional, to the mass functional, over n-3 cycles. And the convergence is a convergence in the sense of de Giorgi, gamma convergence alla de Giorgi, which is a natural notion of convergence for functionals and for family of functionals.
What is adiabatic?
So I mentioned it at the beginning that adiabatic usually is a very general word that means that your system depends on certain parameters, and then you let some of these parameters either go to 0 or go to infinity, converge to something. For instance, in this adiabatic limit, m would go to infinity, but I'll give an even more precise description later on what it means in terms of a certain parameter epsilon that we put into the functional and that we let go to 0. So if you're familiar with the side of the story that belongs to minimal surfaces, this is very similar to what Modica and Mortola did for the Allen-Kahn equation. So for codimension 1 minimal submanifold, it is also similar to what Gerard and Sohner and Alberti, Baldwin, Orlandi did for the Ginzburg-Landau functional, and to what we did together with Pigatti and Stern for the U1 Yang-Mills-Higgs energies. So we prove, and I'll give you the definition later on, that these functional converge in a certain sense that is precise to the area function, of which minimal submanifolds are critical points of. Yes.
So the Calabi-Yau and the G2 monopole equations are going to be dimensional reductions of G2 instantons and 7 instantons, I imagine. And so this epsilon is the size of some circle that's attached on it.
You can think of it as being the inverse of the mass. I don't know if that gives any. So I'm not an expert in G2 nor Calabi-Yau, but this is just the inverse. For me, it's the inverse of the mass. And for instance, this theory actually works for, it doesn't have to work for manifolds with special holonomy. You can just define it for general manifolds. And as soon as you have a calibration, that's where you can actually prove that your limit is calibrated under certain hypothesis. So let me give you more precisely the geometric setup. So we'll be working on a Riemannian manifold of dimension greater than 3, possibly with boundary. And we consider the trivial principal SU2 bundle. So it's just the product between SU2 cross M. And if you don't like thinking about SU2, you can just think of it as being S3. And this is also valid as a Lie group. And in particular, you can also identify SU2 with quaternions of unit norms. You can also associate to a principal bundle, you can associate the adjoint bundle P, which is the following vector bundle that you see here. It doesn't really matter what this definition is, but for our purposes, this is just the Lie algebra of SU2 cross M. And again, if you don't like to think of matrices, you can think of SU2 just being imaginary quaternions. So in particular, elements of the following form, AI plus BJ plus CK, where IJ and K are the usual bases of the quaternions. So in particular, they satisfy this relationship. And if you want a very precise correspondence, is the following one. So if you give yourself an imaginary quaternion, then you can actually translate it back to matrices using these Pauli matrices. So in particular, sections will just be, the sections phi that we'll consider will just be sections of this associated adjoint bundle. So they will be locally with values in matrices SU2 or locally with values in imaginary quaternions. And Lie algebra value differential one forms will just be elements of the following type. So it will just be vector valued differential forms. So these AI, AJ, and AK are just real valued differential forms. So these Lie algebra valued, these SU2 valued differential forms are simply a triple of differential form, real valued differential forms with the bases IJ and K satisfying certain properties that you can see listed here. So this is the geometric setup. I also have to briefly mention that there is the language in which I'm going to describe some of these convergences or some of these limiting objects is the language of geometric measure theory. So in particular, I'll be interested in currents. And if you've never seen geometric measure theory, probably this slide will be a bit too much to digest. But if you've never seen them, you can think of currents as being submanifolds with singularities. And if you know what currents are, then they're just linear functionals over the space of compactly supported differential forms. But in particular, we'll be interested in integer rectifiable currents, so currents that take the following form. So in which the linear functional of the space of compactly supported differential forms is given by integration over sigma, which is a certain rectifiable set, and where theta is integer valued almost everywhere. Currents, the interesting feature is that they can be given a notion of boundary by a Stokes theorem. And cycles will be currents without boundary. Also, to a current, we can actually associate this notion of mass, which for the purposes of the intuition is just the area of the corresponding submanifold. So this is the right notion of generalized submanifold, so submanifold with singularities. Why do we introduce currents? Because these currents have good compactness properties. So it is relatively straightforward to, under certain uniform bounds, it is relatively straightforward to extract a certain limit. And then, actually the crux of the matter is to take this weak object and prove that it is a regular one. So the major drawback is that the regularity theory is hard. It's just, to some extent, the purpose of geometric measure theory is very similar to what we do in partial differential equations when we take weak solutions and then we try to upgrade weak solutions to strong solutions. We do the same thing for submanifolds. But let me give you the variational setup. So for epsilon greater than 0, we define these epsilon Yang-Mills-Higgs energies as being solutions of the following pair phi. The energy of a pair is the following energy, which is very similar to what we had before. There's the Dirichlet energy term plus the curvature of the connection, together with these two scalings in the front. And I'll explain you where these two scalings come. But as before, the dA is this twisted exterior derivative, so twisted by this A, and Fa is again the curvature of the connection. So the only difference with what I had before is that this is taken over a general manifold and that I have this scaling epsilon and 1 over epsilon. So how do we relate the functional that I introduced before without epsilon to the one with epsilon? There's one immediate way to do this is if you rescale the metric. So if you blow up the metric by a factor epsilon or epsilon squared, then you know that the functional computed with the following blowed up metric, so the functional one without epsilon with the blowed up metric is epsilon to the 3 minus n times the functional that you see here. And this is where you see that these two scaling factors, 1 over epsilon and epsilon, are chosen such so that they balance each other out, and you get a rescaling of epsilon to the 3 minus n. N is the dimension of it. Yes. So this is one way to relate the functional without epsilon to the functional with epsilon. There's also another way. Instead of rescaling the metric, just fix the metric, and then you rescale the section. So yeah, you define this new section psi, which is just epsilon inverse phi, and then you have this identity that this functional with epsilon is just the function that we had before rescaled by epsilon. And why is this useful? Because effectively this proves that, I mean, the large mass limit that I was mentioning before is equivalent to taking the limit epsilon equal to 0. So later on, whenever I'll refer, I mean, I'll try not to refer to adiabatic limit anymore, but I'll simply take epsilon going to 0 in the following functional. So you can see here that now we have a family of functionals, E epsilon, that is indexed by this value epsilon strictly greater than 0. And then I take epsilon to 0, and I try to understand what happens in this singular limit. Oh, that I don't know. That is it's beyond my area of expertise. I know that it's just it's commonly referred to in gauge theory. I've seen it plenty of times, but I've never actually asked myself why. Okay, so I want to relate this family of functionals to the area functional. What is the area functional of this generalized submanifold? And the area functional that we introduced before was this mass. So in particular, to actually get a limiting current out of this, I need to associate a current at the epsilon level. And the way in which we get a current out of this object, out of these sections and connections, is as follows. So to every section phi and a, and they don't need to satisfy any equation, we can associate the following real valued 3 form, which is given by, well, this is a 2 form. You wedge it with this 1 form. This is quaternionic valued. I just take the real part of it. And this is a real valued 3 form. So it is essentially just so it's the real part of the exterior derivative wedge the curvature of the connection. So this is how I can associate a 3 form, so in particular an n-3 current by duality, to any section and connection. So these don't satisfy any equation whatsoever. But you can probably, I don't know if it's clear, but you can see that if you take the absolute value and you sort of apply Cauchy-Schwarz or Peter-Paul, then you can sort of obtain the integrand back. So essentially you would get the absolute value of this times the absolute value of that, and then you can sort of split them. So in particular, the following current is bounded by the energy. And this is very important for compactness purposes, because as soon as I assume that I have sections and connections with bounded energy, right? As soon as I have sections and connections with bounded energy, this means that these current have bounded mass. So if I have a family of those, then just by Banach-Alaoglu, I can extract a subsequential limit. So in particular, there's this inequality, and a quick computation reveals that if you satisfy the monopole equation, then you actually have equality between these two terms. So this n-3 current is actually the energy integrand. So these are 3 forms. So by duality, we can associate to these 3 forms an n-3 current. How do we do this? Well, just by wedging any n-3 form, wedging it with the following real valued 3 form. So this effectively gives you, for any section phi, any connection A, gives you an n-3 current. And this current in particular is bounded mass. And this is what I was saying before. So if we have then a family with uniformly bounded energy, these will have uniformly bounded mass. So just by compactness, we can extract a limit. So extracting a limit will not be the problem. Again, this is an instance of the fact that usually proving existence of the limit in this geometric measure theoretic framework is relatively straightforward, and proving regularity is actually the hard part. So If you don't have questions, I'll proceed with the main theorems.
Can I ask a question?
Yes.
Like what's the model solutions or something like can you, when you have some Codimension space minimal surface, can you like close some instant terms along them to
So this is part of one of the main theorem. You're anticipating one of the main theorems, but that essentially there are so-called BPS monopoles that we use as building blocks to actually precisely do what you do. It's because one of the part of the gamma convergence is that you give yourself a cycle and then you want to approximate the cycle. So you can assume that is polyhedral. So in the normal bundle of those things, you put these special solutions. It's exactly that. So a gamma convergence statement. So this statement that this family of functionals converges to a certain limiting functional is usually divided in two parts. There's a limit inequality and there's a recovery sequence part. The limit inequality is essentially a compactness statement that goes as follows. If you consider sections epsilon going to 0 of smooth sections and connections, of course SU2 sections and connections, but this is only SU2, with uniformly bounded energy, and satisfying this technical hypothesis that for now you can actually, you can forget altogether, but then there exists a limiting current, an n-3 current, that restricts, in the boundary of M, restricts to a cycle, so it doesn't have any boundary in the interior of M, such that along subsequences, you have the following convergence. So the n-3 currents that I've defined before converge subsequently to the following current times 4 pi. So that's just a normalizing effect. So in particular, this is integral. So and this is the interesting part. It is also a cycle in the interior because these in the interior are closed, but this is an integral cycle. So it's a compactness statement. But we can also say more because there's also the existence of this measure mu such that the energy integrand converge to this following Radon measure mu in C0 of M star, so in the dual of C0. And in particular, we have the following relation between the limiting current T and this Radon measure mu. So in particular, T can lose mass, essentially. This only says that T can effectively only lose mass. So you can, out of this data of a section and a connection, you can extract two limits. One of them is a current, one of them is a Radon measure. The current is the limit of the n-3 currents that I introduced earlier. The Radon measure is just the limit of the integral Radon measures, and there's this precise relationship between the two. And why is this called a limit inequality? Because there's the following limit inequality, essentially. Because we know that the area of the minimal, the area of the surface, so the mass of the current is bounded by the energy. Yes. Yes, because it's an integral current. Exactly. You know that theta is strictly greater or equal than 1 for almost everywhere. Exactly. So this is one side of the gamma convergence. There's also another side, which is the so-called recovery sequence, which is what Bob was asking earlier. If I have an n-3 current, can I approximate it with these sections and connections? And this is precisely what happens here. So if you give yourself an integral n-3 current, then you know that there exists a family of smooth pairs, phi epsilon and a epsilon, such that the current that we constructed earlier will converge back to it, again, in the sense of currents. And yes, this one. Yes, I want it to be a boundary in the interior for some gluing purposes. And in particular, the area of the limit. So the mass of the current that you gave yourself at the beginning. So the area of the singular submanifold is given by the energy, the limit of the energy. And we also need to satisfy this technical condition, and I'll explain why this technical condition is here. So I explain everything in terms of this so-called monopole functional, right? So this was a Dirichlet energy term plus a curvature term. But when you do this type of phase transitions analysis, there's always, the starting point is a double well potential. So you have always a Dirichlet energy term plus a double well potential. And you can get rid of this hypothesis and the other hypothesis that was named 1 in the previous slide if you just consider the following functional and you assume that the following functional is bounded. So that forces you to be with values in the sphere, essentially. So just to say that, and this resembles more the actual functional that is usually considered in Allen-Kahn or in Ginsburg-Landau or Yang-Mills-Higgs. So a Dirichlet energy term, connection term, plus double well potential. Delta of epsilon is the following, is just, you can take it epsilon to be 3/2. So just for the, but anything between 1 and 2 works. So in particular, this is telling you that the potential doesn't really contribute much to the, analysis. So it's negligible. But in particular, the following two statements were saying that the monopole functional gamma converges to the mass functional. But if you instead prefer to work with a double well potential, if you assume that these are just sections and connections with these new twisted perturbed functional bounded, then this perturbed functional will gamma converge to the n-3 function. And this is with the purpose that we have in mind to actually construct stationary n-3 variables, integral variables, then this function is what you would want to consider. Yes.
So for Allen-Kahn, for gluing, there's usually some non-degenerate assumption. So then if you drop this assumption, then naturally this has some examples of minimal surfaces that are not limits of Allen-Kahn. So how come that it doesn't show up in your setting?
Well, it shows up here. It shows up here, and this is the only thing that you need to, and also this is a, I mean, these are not, this is not minimal if you look carefully, right? This is just an integral current. This is not minimal. So I presume that Mantouli, these examples are minimal. Because this just says, yes, so this just converges to the mass function, right? And then in particular, I have never really requested that phi epsilon and a epsilon are solutions of any equation. I just want them to have finite energy. Yes.
Inequality.
Yes. Yes, exactly. But this inequality, if you remember the sort of computational trick that I showed earlier, this follows automatically because the mass of T is just the L1 norm of Z, but the L1 norm was bounded by the energy. And then in particular, if you just take if you just take the limit that will just by lower semi-continuity of the mass, then you just get a.
So here too, they're not satisfied.
They do not satisfy any equation exactly. So that's why it's only a sequence of smooth connections and smooth sections with uniformly bounded energy. Exactly. Yes. So one is not necessary if instead of working with these functionals, you work with the perturbed functional, but otherwise, yes. Because it's sort of like. Yeah. Other question? And as a very nice application of this gamma convergence type statement, we have the following Plateau problem. So if you consider a smooth n-4 dimensional submanifold of the boundary, and then you can construct families of smooth pairs on the boundary, so family of sections and connection on the boundary, such that, let me actually skip to the important part because this is written in a very cumbersome way for a remark because of a remark that I'm going to mention. But if you give yourself, you can find these smooth pairs on the boundary, psi epsilon and b epsilon, such that for any sequence of pairs, phi epsilon and a epsilon having this boundary condition, and such that the energy is lower than the energy of the infimum, then you can compute this, you can prove that this Z will converge to the mass minimizing current. So you will converge to an integral current. So what is alpha epsilon? Alpha epsilon is just the infimum of the energy. And you can prove that the infimum of the energy converges to the infimum of the mass function. It is written in this very cumbersome way, because the regularity theory of Yang-Mills connections is not understood in supercritical dimension. What does this mean? It means that as n is greater or equal than 6, we don't even know what the definition of weak connection is. So saying that there exist smooth sections and connections realizing a certain boundary data is not known to behold. So that's why it's written in this way. But the main takeaway is that if you give yourself a gamma in the boundary, then you can essentially prove that these currents, n-3 current, converge to T, and T is the mass minimizer. So it's the solution of the Plateau problem. So let me give you this definition of what generalized monopoles are, because this is interesting from the perspective of minimal surfaces. What happens to this side of the story that is the Donaldson-Siegel program? So if M in particular carries a calibrating n-3 form, let's call it theta, then we'll say that phi and A satisfy the theta monopole equation if they satisfy this version of the monopole equation, right? So it's just the dual of the A of phi is just equal to f of A wedge theta. And there's also a rescaled version for epsilon. And the particular setting that I've mentioned earlier were the one of the G2 manifold, in which theta is the so-called co-associative 4 form. But you can just imagine that this is a very precise geometric setup in which you are given a calibrating form. And there's also Calabi-Yau monopole, so you are on a Calabi-Yau threefold, where theta is just the real part of the holomorphic volume form. So these are two specific geometric setups in which you're given already a calibrating form. And the Donaldson-Siegel program predicts the following two things: that in the mass going to infinity limit, you should converge to co-associative submanifolds. So essentially the current that I mentioned earlier are calibrated. And in the large mass limit on Calabi-Yau monopoles would converge to special Lagrangian submanifolds. So what does this all mean? It means that in this very specific geometric setup in which you are given a calibration, the limit is calibrated. So in particular, the natural question at this point is that if we take sections and connections as in the previous setting, so pairs phi j and aj solving this epsilon monopole equation, under what condition do we have that the limiting current T is calibrated by theta? And does this always hold for G2 monopoles and Calabi-Yau monopoles? And we have a very interesting corollary in this direction. So if you consider sections and connections satisfying this generalized monopole equation, where theta is the given fixed calibration, and if you write this time, so if the energy measure is slightly different, because I have to take into account the fact that these satisfy a different equation, but this is simply, this is very similar to what we had before, except for this extra term. So if you have this equality, then the weight measure will satisfy this. And in particular, you have equality in between these two if and only if T is calibrated. This effectively is saying that you have two terms in the monopole function. We have the Dirichlet energy term, and we have this curvature of the connection term. If there's equipartition of the energy between these two terms, then the limit is calibrated. It's an if and only if statement. So this is the main takeaway. If you have this equipartition of the energy, then you are calibrated. Of course, proving that there is this equipartition of the energy more generally. So this is something that is known in the setting of Calabi-Yau threefolds and G2 manifolds, thanks to the work of Yang-Li of last month. For a general manifold, for general critical points on a manifold, this is not yet known. But this is something that is usually very useful, has been very useful for this Allen-Kahn side of the story, and also for this Ginzburg-Landau. So for the Codimension 1 setting and Codimension 2 setting, similar equipartition of the energy phenomena are actually extremely useful when one tries to extract information on the limit. Okay, let me give you some elements of the proof of the limit inequality, some elements of the proof of the recovery sequence. I'll finish with some open questions, and then I'll let Renato take the lead. So the limit inequality, as I mentioned a couple of times, extracting a limit is relatively straightforward, right? Because if we take a family of sections and connections with uniformly bounded energy, then just by Banach-Alaoglu, by duality, is relatively straightforward to obtain a limiting current, right? So we have in particular, we have the existence of a current T satisfying this. So the actual hard part of this work, or at least of the first theorem, is to prove that this current is an integral current. So in particular, that this current takes the following form, where theta is in particular integer valued. And just by, I mean, integrality again is a local property, then we can just reduce it to the case in which M is just a cube, and we introduce this current. Sorry, this map. The map that takes your manifold, so your cube, your n-dimensional cube, and just gives you the first n-3 components of it. And what we want to do is, instead of working with the actual current T, we work with slices of the currents. And then there's a result that is in various forms due to Brian White, Gerard Sonner, Ambrose, and Kirkheim, saying that if you understand well the slices, then you understand the full current. And in particular, it is this. If you take a current, you know that this current is integral if and only if every slice is an integral current. And this is extremely useful because it allows to reduce proving integrality of the following current in an n-dimensional manifold to proving it on a three-dimensional cube. So then the crux of the matter is actually just to prove the statement in 3 dimensions. So you reduce it in generality. So just no. You reduce it to 3. This would be 4. So you project it over the first 4. Oh, sorry. Normal means that the mass of the current and the mass of the boundary are just finite. Say again?
The mass of the current and the mass of the boundary are
Finite. So normal in the sense of Federer. So let me just give you a couple of ideas for the recovery sequence part. So the building blocks for the recovery sequence part are these objects that Bob already mentioned earlier. So these Bogomolny, Prasad, Sommerfeld monopoles, which are special solutions of the monopole, they're special monopoles that they take the following form. So phi 0 is the following function, is the following section, where again I'm identifying imaginary quaternions with just R3. And in particular, the connection takes the following form. So these are special solutions of the monopole equation with just energy equal to 4 pi. And we use these as building blocks. We use them as building blocks in which way? So give yourself a current. So remember that we want to, given a certain current, we want to approximate it, or we want to construct sections and connections such that this Z will converge back to it. So in particular, given a current is in the statement, you can approximate this current by a polyhedral current. What is a polyhedral current? Is just a current that is given by a polyhedron, essentially. So just faces glued together. So it's really just a polyhedron. And this you can assume that this polyhedron has multiplicity 1 on each face. So it is really just what you would think of as being a polyhedron. And again, this is because if one of the faces were of higher multiplicity, you can approximate it with just faces that have multiplicity 1 close enough. Then, so you have to imagine that now we want to approximate this polyhedron. How do we approximate this polyhedron? Well, you essentially, it becomes a gluing procedure. So in the normal bundle, take each face. In the normal bundle, you will put rescaled solutions of these rescaled solutions, so rescaled BPS monopoles. And then you just have to make sure that as you glue along the edges, you're gluing things correctly. But this is the underlying idea. So you have a polyhedron. In the normal bundle to each of these faces of the polyhedron, you just put rescaled versions of these BPS monopoles, and then you just glue them along the edges. And this provides you with the sections and connections that then you need to approximate the limiting current T. So let me conclude with a couple of questions. So this is a theory, this is a gamma convergence theory. So we effectively proved that these functionals indexed by epsilon converge in the limit to the mass functional, so the area functional over the singular submanifold. So this is a theory for minimizers. But what happens if we have general family of critical points? So an interesting question would be the following. If you consider a family of critical pairs for these energy functionals with, let's say, uniformly bounded phi and uniformly bounded energy, such that again this specific condition is, this specific hypothesis is satisfied, then do we have that the following measure, so when we pass this measure to the limit, do they converge to a stationary rectifiable n-3 varifold? So there's plus a certain diffuse part. This is extremely reminiscent of what happens for Ginzburg-Landau. As you let these measures go to the limit, you actually converge to a diffuse part, which would be this part that is n-dimensional, plus the weight measure of a stationary rectifiable n-3 varifold. So in particular, can we upgrade the theory that I've explained so far for minimizers to a theory for general critical points? Can we get stationary varifold out of it? And then the natural question at this stage would be, if this works, do we have that the following varifold normalized suitably is an integral varifold? So the same thing that we had before. So before we had we could extract a current. Do we have that this current is integral? And the same question happens here for the following varifold. And finally, what can we say about this Donaldson-Siegel program? As I've mentioned, there's really interesting work of Yang-Li, which effectively carries out part of this Donaldson-Siegel program, but the Donaldson-Siegel program actually would be an equivalent of what Taubes did. So even just to begin approaching that, we would need to identify the right invariance that we want to then compute as invariant in terms of invariance over these co-associative and over these special Lagrangians. And so these are the following questions. So we're currently thinking about the first question, but these would be extremely interesting, especially if you're interested in the minimal surface side of it, because once you have an integral varifold, then you could hope to run a regularity theory. Of course, this is just a hope, because the regularity theory of minimal submanifold is in higher Codimension is extremely hard at this stage. And well, this finishes what I wanted to say. And if you have questions, I'll take them.